All right, folks. Um, Hope you had a good weekend. Um, Hope you're in good spirits. We're going to start a new chapter. A new chapter is chapter 17. It starts to deal with light and how light waves work and stuff like that. So today, kind of your standard intro day. I'm going to talk you through the kind of physical properties of light and tomorrow we'll have some homework stuff. We'll have a little bit of a lab that we'll run through as well, and then we'll kind of just roll from there. So, like I said today, I just got to kind of survive it. I'm going to get through and I'm going to teach you some stuff about how light works. So, here we go. All right. So, when we look at light, light acts like a wave. All right. We always wonder what kind of wave it is. It acts like an electromagnetic wave. All right, which is really, really different for us, I suppose. Um, if you look on there, on the animation there, you're going to see it does have a standard wavelength. That's not something that is going to change for us. The wavelength actually becomes somewhat important for us when we measure it and look at it. You're also going to see it's got an E and a B. Now, if you remember back to previous chapters, that B, as it's moving there left and right on that x-axis, that B is the magnetic field. All right. The E, as it moves on the z-axis, so to speak, that E is our electric field. So these are things that we've talked about a little bit beforehand. Remember that E field, like we talked about, between two parallel plates. That that B field was again that magnetic field, kind of like the Earth had, right, where we saw it move because of those electric charges and stuff like that, right? So again, it's a combination of the two for us. It has some unique properties that we haven't seen before. All right. Um, so we asked, what starts electromagnetic waves anyway? Right? Somewhere, an electric charge is wiggling around. We'll call it oscillating, right? Wiggling, not a real scientific term, so we start to use the term oscillating. All right. Now, that could be, in a straight line. That could be through, a different form of, you know, physical material of some kind. There's all kinds of different ways to get an electric charge to, I guess, oscillate for us. All right. So this describes a moving electric charge, right? Because if it's wiggling or if it's moving around, um, and we see a moving electric charge, we produce a magnetic field, right? Now, here again, we talked about this, right? When we said that we had a wire. A wire can produce a magnetic field, right? If you remember right hand rule, where we all of a sudden had to have thumb going in a specific direction and fingers wrapping around and stuff like that, that produced a magnetic field. All right. So did it produce electromagnetic waves? Yeah, kind of. All right. Um, because in this case the electric charge is oscillating, it produces a changing magnetic field, and that's where we get a little bit of the difference. All right. Because it's getting moved around in different directions, that's where we're able to see this kind of creation of a changing magnetic field. Um, and as it turns out, changing magnetic fields produce electric fields, which are weird. I mean, that's a weird outcome for us to be able to get to. And the reason why is, let's take a look at this first. So a simple antenna is essentially just a wire. A basic antenna works by continually switching the direction of the current. By doing this, it causes a fluctuating magnetic field, which in turn causes a fluctuating electronic field. All right. So what we see is something along the lines of this. Alternating current is fed into the antenna. The electrons move back and forth, making a fluctuating electric field, which in turn creates an alternating magnetic field, right? Now, for most of us, I suppose, it's been a number of years since we've actually had to use the byproduct of an antenna, right? I remember as a kid growing up, we didn't have Apple Music, Spotify, Pandora, XM, anything like that. And so we listened to the radio. So we knew what radio stations we liked. And you've probably heard the story that, we were going out to South Dakota one time, and we're in the middle of South Dakota, which if you haven't ever visited is absolutely gorgeous, except the opposite of that. There's not a lot there. And so we're driving through late at night, trying to make it to our hotel that we're going to stay at. And all of a sudden we get um, radio station from my hometown, which is in Eau Claire, Wisconsin, or near Eau Claire, Wisconsin, right? And it's just like, what the heck? Well, here they had their antenna was one of the strongest in the areas, which meant that their radio signal traveled very, very far. In that case, it hit the perfect scenario where it actually transmitted way out there. All right. So when we see this alternating current through there, I remember driving by the radio station at another point in time later on in my life and seeing, these radio towers that are, hundreds of feet in the air, right? And that's how they generate a radio signal. Is they just send an electron up and down, alternate that current, and all of a sudden now you can get a frequency, and you can create a wavelength that's conducive to you hearing whatever music you like. Hopefully it's not country, but if it is, I suppose that's okay for today, right? Um, but I mean, even if you think about outside of an antenna, right? If you think about like a light bulb going through there, you're going to produce an electromagnetic wave there. For us in that one, we're going to be able to see that, right? If you got a compact fluorescent bulb, right? Inside of there, you're going to have gases that react when or get excited when electricity goes through them, right? Uh, Same thing's going to happen if you've got incandescent bulb, right? Little filament in the inside going to run between there too. So that's how we're able to see light in kind of our world. Um, Another example for you to look at, you can see the B fields in the middle, right? Getting flipped and getting moved and getting turned around. That produces that E field, which changes direction up and over the top or down and around the bottom, whichever way it goes there. All right. So this becomes the interesting part of it, right? A fluctuating E field produces or induces a magnetic field, which in turn, the magnetic field induces an electric field. And by this oscillating, this flipping, this role reversal, what happens is we see that this is how we're able to make those electromagnetic waves happen for us. Just this changing. One changes into one, the other changes back to that one. One changes into the other, so on and so forth, and so on and so forth. Okay? When we look at the property of waves, these still do apply to what we're talking about here, right? We're still using the concept of wave speed as frequency times the wavelength, right? Frequency is still going to be measured in hertz. Number will be a little different this time, though. Speed of sound, even though we could get it going pretty fast through a solid, it still doesn't compare to that of a light wave. It'll be our amplitude. Amplitude, remember, that's how big the wave is. Like that's the size of the trough or the size of the crest or the depth of the trough, right? This is just how tall the wave will be for us, all right? Wavelength, distance between similar points, right? Again, we saw this one as well. And then V, that's just our wave speed again, all right? It's still going to be measured in meters per second for us. So, something to be aware of, light does travel at different speeds in different mediums. And so did sound, to be honest, all right? Sound had a relatively specific speed through air. If we made that air thicker or thinner, meaning hotter or colder, it changed. As it went into liquid, it went faster. As it went into a solid, it went the fastest, right? Now, light, as it travels at these different speeds, the frequency of it isn't going to change. So if the frequency does not change, then what that means is the wavelength has to, okay? Electromagnetic spectrum, now don't write this down, just take a look at it and see some of the stuff that we're talking about here, all right? When we start to look at a radio wave, we see the radio wave, the length of the wavelength of it is long. It's about 1,000 meters long, right? Which should make sense. if you're thinking about how big a radio antenna is, it's hundreds of feet tall. Okay, so because of that fact, then what we see is if it's got a longer wavelength, it's going to have a shorter frequency, right? So it's not going to be traveling as fast. So these are going to be long, slow, looping waves for us, all right? A microwave, I know that sounds weird, but yeah, that is the thing that's in your kitchen. But back in the day, back in, I think it was World War II, uh, those were their radios. They would have not a microwave like you see in the back, like in your kitchen, but they had a way of being able to use those to communicate with people. All right. Infrared, right? Visible, ultraviolet, X ray, and then there's the gamma. Okay. For us, when we look at a gamma, it's going to have a short wavelength, 10 to the negative 12 meters, right? Its frequency, it's going to be very high. We're going to get a lot of waves per second, a lot of oscillations per second with that one. Okay. And again, for the most part, we likely live in that visible light world, just because for us, that's the way that our vision is able to work. All right. Above that, below that, we can't necessarily, right? And again, you've heard of ultraviolet, the UV stuff. You've heard of X-rays, UV from the sun, X-rays from machines to see if bones or something like that is in a bad place. Okay. Infrared, again, heat, stuff like that. Okay. So the transmission of light through a medium. This one is something that's going to be a little bit different than what you expected. So the speed of light is 3 times 10 to the 8th meters per second, 186,000 miles per second. Speed of light is super, super fast. If you've ever been to a fireworks show, what you know is if you're sitting far enough away, there's definitely something different there, right? Speed of light, going to get there instantly. Speed of sound, it might take some time. If you've seen lightning off in the distance, right? The old wives' tale is that you can look at the lightning, count how many seconds, and that's how many miles away it is. It's relatively true, right? And again, you see that light instantly because it is traveling very, very quickly, but then the sound catches up, right? You've been to a concert and all of a sudden you got the cheap seats where you're so far away. You can watch on the video monitor. You can see their lips moving, but all of a sudden it's out of sync because the sound's taking a bit to get there, right? So light only knows to travel at that speed. Okay. When we talk about the speed of light in a vacuum, we're talking about it in outer space, right? Now, within outer space, if we were able to say, you know what, I want to talk to the person that I'm doing a spacewalk with, and I don't want to use the radio because I want to be able to tell them something. If you were able to survive the temperature and if you were able to survive the lack of air pressure there, because the temperature is about 2 or 3 Kelvin, air pressure there is about 0 ATMs, right? What would happen is that if you were to expel that sound wave, there'd be nothing for it to vibrate because in that vacuum, there just isn't air. There's nothing. It's just a void of space, right? So when we see this, light can travel through this vacuum because of the 3D nature of it, because it is an electromagnetic wave. So what happens is that that's the only speed it knows. It's just fast, right? So even when light travels slower, it's not really being slowed down. And this is the one that I like to leave for the end of the lecture because most of the time people are like, what, how? Well, the reason that it works is it's being caught and released. Well, what does that mean? So if light's an electromagnetic wave that only travels through a vacuum, right? It's basically energy, radiation, if you want to look at it that way. All right. So what happens when it encounters an atom? Well, the thing is that it gets absorbed by the atom, right? As it gets absorbed by the atoms, the electrons in it vibrate for a very, very short time. So think of it this way, right? I don't know if you talked about thin line spectra in chemistry, But if you excite an atom, what it does is the electrons jump to a new energy level. As they jump to a new energy level, what happens is once they get unexcited, so to speak, a bad term, sorry, they'll drop back down. As they drop back down, they release a burst of light, right? Well, that's really what's taking place here. Now, granted, we're not going to see necessarily a different burst of light because we're seeing nitrogen, we're seeing oxygen, we're seeing CO2 and other stuff, right? For us, it's as simple as just saying it's getting absorbed, getting shook, and then letting it go. All right? So then the atom hits another one. Okay? So here's what it kind of looks like for us. All right? So what we see is that light wave hits that atom, starts to get jacked up a little bit. That atom starts to move around a little bit, releases it again. The one in the vacuum on the bottom is able to travel at just a steady speed. So it travels at c, gets absorbed, travels at c, gets absorbed, and then travels at c. Whereas the bottom one, that wave just travels at the speed of light. Okay? So that light wave, as it's coming from, say, the sun, right? It's going to go through the vacuum of space. As soon as it hits the atmosphere, it slows down. Now, 3 times 10 to the 8th, it'll slow down to about 2.995 times 10 to the 8th. So it's not a hugely appreciable difference for us, right? So if all of a sudden our atmosphere gets real thick, right, yeah, it's going to get it slowed down. But even on a cloudy day, is there still light during the day? Yes. The reason is because it's filtering through there and then it keeps going down. Now, can we stop light? 100%, right? If you've got the curtains that are the blackout curtains, right? That's going to completely absorb that light and just shut it right down. Okay. If you look at water, water absorbs it. It slows it down, right? There are regions in the ocean that the light can't get to. The reason being that light hits the ocean water, absorb, release, absorb, release, absorb, release, absorb, release, right? After a while, it just runs out of energy. You know what I mean? It just can't do it anymore. It just loses all of that oomph, so to speak, and eventually gets absorbed and doesn't get released, right? So when we look at light, light will have different speeds. And we'll talk about those different speeds if it's through glass, if it's through water, if it's through something like that. Okay? But know for us that really light is going to be 3 times 10 to the 8th, that meters per second. That's a new number for us to be able to look at. Okay? Thanks for bearing with me today for me to be able to get out kind of the entry level stuff and the beginning stuff and all that information. Tomorrow we'll start working on some more stuff. Otherwise, you survived the lecture, so hope you have a great day. You don't have any homework today. Today was just basically meant to listen to lecture, pick up some stuff there, and then we'll go on from there. Okay? All right. I will talk to you tomorrow. Hopefully you have a great day. Take care of yourselves, all right? See ya.